Hello, everybody. We're going to jump right into section 4.1. All of section 4, we're going to talk about derivative applications, uses. Why do we care about derivatives? What can we do with them beyond what we've already seen? Okay, and so we're going to start by talking about something called minimum and maximum. And so just to get some quick definitions out of the way, when we talk about what's so-called extreme values, the largest or smallest values on a graph. Okay? So, absolute extrema, the absolute max or min, where this absolute means only one, right? There can only be one absolute max or absolute minimum. And on a graph like this, where we have this hard stop, we call this point right here would be absolute max, because if you compare this to any sort of other point on the black graph, this one is the absolute maximum. Now, I will say there is no absolute minimum on this graph, because it's going to continue downwards forever according to this arrow. Okay, so you're not always guaranteed to have an absolute max. Some graphs have them, some graphs don't. But what we're also going to be interested in are points like this, which we call a relative min and a relative maximum. Okay, which is this point right here does not beat this point, but it beats a point around it. And so you can imagine if you just took a square rectangle viewpoint, if you couldn't see anything outside of this box, you would think that this point right here was the absolute max. And any point that satisfies that criteria is called a relative extreme, a relative maximum, or a relative minimum. Notice if I make my window right here, you don't think that there's an absolute maximum. Just looking at this window, you would kind of believe, oh, this side is going to keep going down and this side is going to keep going up. It's only when your box contains one of these, what we call peaks or valleys, that we're willing to call it an absolute maximum and an absolute minimum. Okay, so the question is, how do we connect this concept to derivatives? Okay, so if I were to, let's say, take a look at a graph like this, and, for just clarification's sake, let's say we also are only going to take a look at it on an interval. Okay, so let's start labeling some pieces. Right here, this is a relative maximum. Right here, we have an absolute maximum. Right here, we actually have the absolute minimum. And what is this? Not special. Not worth naming. Nothing about it actually tells us its name, right? And so that's looking at it graphically. But it turns out there's something really interesting going on when you take a look at the derivative. So let's just sort of ask ourselves, what is the derivative sign for each of these values? So notice, as we go from this point to this point, you hopefully agree that the black graph is increasing, which means the derivative is going to be positive. And if we keep going from the relative maximum to the absolute minimum, hopefully you would agree, because it's a decreasing graph, the derivative sign will be negative. And one more, as we go from this point to this point, we're increasing again, we're back to being positive. Now, what is happening exactly identically at some of these points? Well, if we draw a tangent line at these relative minimums and relative maximums, you're going to get a flat, constant line where the slope is 0. Which also tells me that the derivative, and I'll just, for argument's sake, I'll call this point A and I'll call this point B. F prime of A is going to be 0, and F prime of B is going to be 0. We call these points critical points. X is a critical point, and sometimes we call it X sub P, if F prime of XP is 0. Technically, OR does not exist. We're still interested in that, but we'll talk about that one in a later video. But for right now, we're just interested in where these critical points sort of look. So let's take a look at a different graph, but this time I'm not going to graph it. Let's do like 3x squared plus 5x minus 1. And what are the extrema? Now, once again, if you graph this, that question is answered pretty concretely, you know, if you can get a good enough graph. But the whole point is there something that we can do procedurally, algebraically, to find that same extrema value? And so what we're going to do is we're going to, step 1, we're going to find critical points. So remember, a critical point is a point where it says f prime of x sub p equals 0. Well, do we know f prime? We know f prime of x. If we do the derivative operator, 6x plus 5, and we'll just set that equal to 0. Minus 5, 6x equals negative 5, divided by 6, x equals negative 5 over 6. Now, we know for sure this is a critical point. But what we don't know is we don't know what type of critical point is it. Is it a relative maximum? Is it a relative minimum? Is it an absolute maximum, or is it an absolute minimum? That's where step 2 on this process is going to come in. We actually have to plug in values and check what type of values we get. And specifically what we're going to do is we're going to plug in values on the number line. Okay? So, we go to a number line. Sometimes this is called the first derivative test. And we know that negative 5 over 6, that's important. So we're going to test some values. And let's test some values around it. Let's go something to the left. You know, this is almost negative 1. So let's do f prime of negative 1. So as a reminder, f prime is 6x plus 5. This would be 6 times negative 1 plus 5. Negative 6 plus 5 equals negative 1. The slope is negative, so we know that this whole interval is decreasing. So we know it's decreasing from negative infinity to negative 5/6. Same thing, let's choose something on the right. And let's go way easier. Let's do f prime of 0. Right? What's that going to be? 6 times 0 plus 5 is 5. All I care about is that it's positive, which means the graph is increasing. So negative 5/6 is a critical point where, if we look at the graph, let's call this negative 5/6. Here's what I know. I know a little bit to the left, we're decreasing, and a little bit to the right, we're increasing. So what does that make this critical point? It's an absolute minimum. And again, this was done without taking a look at the graph. Now, if you know anything about quadratics, you probably could have figured this out on your own. But the whole point is that the derivative operator allows us to find critical points, and critical points are necessary and important to find these maxima and minima, especially when we want to do it without looking at a graph, which is normally what we want to do. I mean, graphs are good, and I'll never claim that they're not good. But we are always interested in finding these. Okay, let's do a much more difficult example. So let's say g of x is x squared times the square root of x plus 1. Okay, so remember, step 1, we're going to find the critical points. Let's take a derivative. This is going to be product rule. We have the first times the derivative of the second plus derivative of the first times the second we're going to try and set that equal to 0. If we go back to, this will be, x squared over 2 the square root of x plus 1 plus 2x times the square root of x plus 1. Something that we can do, both sides of this equation, we're going to multiply by the square root of x plus 1. So this will be x squared times the square root of x plus 1 over 2 the square root of x plus 1 plus 2x times the square root of x plus 1 quantity squared. On the left-hand side, that goes down to 0. Sorry, that goes down to 1. And on the right-hand side, the square and the square root cancel each other, giving us x squared over 2 plus 2x times x plus 1 equals 0. And now it's just in the land of algebra, and we're just trying to work it out. So this is x squared over 2 plus, distribute the first one, 2x squared plus 2x. Let's combine these together. We can rewrite this 2 as 4 over 2, and this is 1 over 2. So altogether we get 5 over 2 x squared plus 2x equals 0. Factoring out an x, and I think we can agree that there's going to be two choices. X equals 0 is a critical point, and 5/2 x plus 2 equals 0. Move over, 5/2 x equals negative 2. I'm just subtracting over the 2, and then we'll multiply by 2/5. We get x equals negative 4/5 is a critical point. So we got two critical points, x equals 0 and x equals negative 4/5. Okay, let's try to see if we can define what type of critical points these are. This is step 2. So we go to our number line and we go, okay, here's 0 and here's negative 4/5. So we got 3 things to check. We want to check here, here, and here. And we just have to pick one number inside these intervals. I would always go with a whole number that will plug into f prime. So we'll do f prime of something, f prime of something, and f prime of something. So let's go, what's something bigger than 0? I think the obvious choice, let's go 1. So what is f prime of 1? F prime of 1 is going to be, if we go up to our definition of the derivative, I actually like to go back to the original. It's a little bit easier just to use. So remember, this was 1/2 1 squared times the square root. Actually should be over the square root, divided by the square root of 1 plus 1 plus 2 times 1 times the square root of 1 plus 1. Now, here's the important thing. You can fill this out in a calculator and you can get an exact answer. All I really care about, notice this is going to be 1 over 2 times the square root of 2 plus 2 times the square root of 2. I don't care what this value is exactly right now. All I care is that it's greater than 0 and it is positive, which means To the right of this critical point, the function's derivative is positive, which means the original function graph is increasing. What's happening between negative 4/5 and 0? This is a little bit harder. This is where it's probably better to go to a calculator just to make sure. Let's pick something between negative 4/5 and 0. Let's go with maybe negative 1/2. What is f prime of negative 1/2? This one I am going to put into my calculator. Plus 2 negative 0.5 times the square root negative 0.5 plus 1. And I do get something negative. Specifically, I got negative 0.53033000859. All I care about is that it's negative and then positive, which allows me to label this critical point. If you decrease and then increase, this is some type of minimum. Now, is it the absolute minimum or the relative minimum? That I don't know yet. When you have multiple critical points, one of them might be the minimum or the maximum. You might need to check that specifically. But right now, I can tell you it's a minimum. Is it the only minimum? Then it probably is the relative minimum, although depending on what the rest of the graph does, you might see something a little bit different. Now, we're going to run into a problem if we take a look at something to the left of negative 4/5, because please note, if we go to the original, x must be greater than or equal to negative 1 due to the square root of x plus 1. So we can't choose negative 2, but we can choose f of negative 1, I will point out. So let's plug that in to our derivative, g prime right here. So this is going to be negative 1 squared times a half times negative 1 plus 1 to the power of negative a half. Ooh, and you know what? Very first thing, we're going to get an error. Because we're going to try and divide by we're going to try to divide by 0. Which means something really, really special is going on to the left. It might be worth jumping to the graphical definition. And if we graph the original, which was x squared times the square root of x plus 1, I'll bring it over in just a second. We can't choose f of negative 1, but we can choose, let's get closer than 4/5. Let's do negative, let's get really, really close. Let's go negative 9/10, right? That should be a little bit closer because this would be negative 8/10. So just one more, a little bit closer. But the important thing is you're going to get something positive, okay? So what does that mean? What am I guessing that the shape of this graph looks like? It's increasing, decreasing, increasing again. I'm looking at something that I'm assuming looks maybe a little bit like this. Now, where is this point and this point and this point exactly? I don't know. But this is my preliminary sketch. And if we bring over the actual graph of x squared times the square root of x plus 1, you can see very clearly we do a little bit of increase, a decrease, and then an increase again. So what are the exact points that we've determined? Is this a relative min or an absolute minimum, or is this a relative maximum or an absolute maximum? Here's what I can tell you, is that this, because it's increasing and then decreasing, this is a maximum. I can tell you for sure it's only a relative maximum. Why? Because the right side of this graph is increasing forever. And that means any maximum that I achieve here, it will eventually get beaten out by this. So, combining this with the graph is a very powerful technique. Critical points are an important diagnosing. As a reminder, we're trying to diagnose functions based on derivatives. And the maximum minima is just one part of that. If you have any questions, please let me know, and I'll see you all in the next video.